thanks for having me here. And it's a really work in progress. So any comments, any idea, any suggestion that you have, it would be great. And I would love how to develop and see how I can finish this project. So let me put in large screen. It's a joint paper with a co-author. We wrote many things, both in combinations and calibration that I will make clear more later on. Roberto Casarin, and Dario Palumbo, that is a bit younger researchers, spend some time in Cambridge, and then we collecting back and we will see what we will do later on. So I thought, I was coming to UK, and it was eventually, because maybe it happened twice in my life, and I thought to start with this picture to motivate the work. So there is this idea every time you spend the summer in UK, particularly in England, North England, there will be a lot of rain, and the prediction, the math, is making easy their own life. They always forecast it will rain. And then every now and now, some summers, for example, 2013, but I remember even 2006, if I'm right, or 5 or 6, one of these two, it was exceptional good, the weather and a lot of sun and a great fun. And of course, the predictions were a failure. So the idea is forecast failure and why this is happening and what could happen. How can we improve that? And we will discuss two ways that I believe can help in this direction. And the first one is a combination where I did some work back in the past. And what is the basic idea behind that? When you have a lot of model, maybe once we were used to select one of them. Now we try to have a different approach. And we try to combine the information from all these densities, and this seems to help the forecast accuracy. And this goes back from 60 years, and it has received quite a lot of attention in the last 20 years. Just another, here I have a really core summary of the key things, and then I will spend more time on the topics. But I wanted to introduce the idea and hopefully relate to literature and present the results. What we also learn, I think the COVID is a great example, that when there are particular situations, the accuracy or the stability of the forecast, if you allow me to use this word, varies over time. So there are models that do better in some periods, others that do well in other periods. So as we do with the parameters inside the model, we should do the same also with the combinations. And the idea is why we don't estimate the time varying weights. So weight is what we associate to one forecast. Why this should be constant and should not vary. And there is a bit of literature in this direction. Then, in particular, the weather literature, but it's becoming more and more important. Combination and also the idea of time varying weights refers usually to relative performance. So one model relative to the other. Before I say the best model versus a combination of them, then I say the best performance in one period versus another period. Calibration is a different idea. And it refers to absolute property of the prediction. And in particular, in our interest now, I start to talk more precisely of density forecast. So we're not talking anymore about only point forecast, but I wanted a complete distribution. And what, in particular, Geithning, together with Aranja, has done in a series of papers, he said, okay, we should look at calibration and density calibration. And if we are not well calibrated, we should consider a recalibration of them. We should change the properties of the density. And I will be more clear later on. And myself did a paper published a couple of years ago, where we did combine the two sets of literature, combination and calibration. So we didn't make them two different contributions, but we put together, but in a static weight. So the weights were not dynamically changing over time. So you know where we are going probably already now, and with this slide, I hope it's clear what is the contribution of this paper. We apply dynamic combinations when calibrating models. And how do we do the dynamic, so the time varying part. We use a score-driven dynamic model. I will provide more definition what is score-driven, but basically you have a loss function which is characterizing the model. Could be likelihood, partial likelihood. There are also other ways. We will work with the likelihood, but you could also think other loss function of interest. And you see how this is evolving over time. You compute the score, which is nothing more than a first derivative of this loss function that you have in mind, and you see the evolution of them combined with an error, how it drives the process. So it's a latent process that you make observable by this score-driven process. And precisely to our model, because since we have time-varying weights, which are fitted to by an observation-driven model, where, as I was mentioning before, the score is what is driving the movements in these weights, and we assume the conditional likelihood what we learn over time. So we are trying to maximize over time the conditional likelihood. We have a process to do that, and by learning how this is going, we will have time-varying weights. So here is the model basically. So the idea was introducing the dynamic component in something that already exists and modeling in an efficient way via the score, because otherwise estimating completely probably will be a nightmare or even not possible if the set of models is large or too large. Then the second part of the title, climate prediction, and we thought where this could be one of the most relevant application for the problems we have in mind. And we decided to focus on wind. Why? There is a large focus, obviously, on the green and how we should change how we produce, for example, electricity, but not only electricity. More generally, electricity markets are highly related to the challenge we have to keep under control the global warming. And in many countries, strangely, I would have expected UK much more front-leading and more similar to Denmark. I mean, there is a lot of wind power, of course, but it's not such as could be the Netherlands. But maybe to the Netherlands more similar, but definitely not to Denmark. Anyway, wind is one of the options that we are considering because, of course, there is an initial cost, an initial pollution to build the windmill, but after that it's a completely green electricity because there is nothing to burn or to produce which is not naturally driven. But there is a big problem. The wind is not stable and it can change very fast. And if you know a bit about electricity markets, you might discover that, or you might know that the markets are structured such as that there are different types where the characteristic of each of them is when the electricity is delivered. Most of us, in terms of research, knows the day-ahead market. So you bid today for tomorrow. But there are also more important continuous markets, such as, for example, the continuous one, which is bidding every 15 minutes to be precise. Sorry that I had my mail open. And wind powers do not participate to this market. Their participation is extremely limited. And there is a reason for that. There are very large penalties in case of non-delivery on this continuous market. Much larger, the penalties are much larger than on the day ahead. And where, for example, I don't know, hydropower or even solar power might have a problem in the mid or long term, but definitely not on the 15 minutes, the wind seems to have quite some challenges and more challenges in the short term than in the long term. So that's why we decided to focus on a 15 minutes wind speed prediction exercise. And what we do find, obviously, if I'm presenting here, you might believe that I'm improving the forecast accuracy relative to standard models for wind speed prediction. So that's minimum result. And basically, what we are learning in this exercise? We do see that, let's focus in particular on the calibration. We do see that the calibration is working to, in the example that we have, to increase the values or to predict better high values in certain hours of the day. So basically, the individual models are too conservative, probably because they don't expect so random changes in wind speed. And what the calibration is doing is pushing higher these values, and is doing better in that. So we think that this is an interesting result, because maybe we'll push forward wind powers or windmills to participate more actively to continuous electricity markets and not only to the day ahead. So here is, if you have that, remember, dynamic combination calibration, application to the wind, short term, our result indicates that there is a value, and in particularly, we should believe more on the wind if you want, and have even stronger wind speed predictions of what the models are. We are too conservative eventually sometimes on this prediction. Okay, now I hope you follow me in these 10 minutes, at least you have an idea of what I presented. Now I can go a bit more in details. And I was sometimes sloppy, so let me try to be precise. And the first thing that I would like to introduce is the idea why we want forecast. I think that's easy. We all agree that it's important to try to predict the future, at least of some variables of interest. But why should I need complete predictive densities and not just a point? And there is we like to have a full distribution. That's what we look as statisticians and econometricians. But remember that the main issue about forecast densities or complete predictive densities is that density is never observable, even exposed. You just have realizations. You don't have a density. And adding realizations does not mean that you know or you have the true density, because there could be changes over time, over observations, or what is. So the main point is, okay, it's fine to build on densities, but how to evaluate them? Who is telling me that is a good job or not? So let me take this simple exercise. The series in red is the variable I would like to predict. And I use the model 1, which is in blue, to predict that. And I use point forecast. And you see the red is moving a lot. It could be stock markets, returns, for example, something similar. And the blue is the prediction, which more or less is the mean. Let me take a second model, the black one. And you have slightly different predictions. So the natural question will be, which of these two do you prefer? Model 1 or model 2? We have the realization, we have the two forecaster. Graphically, if you look carefully, you will see a difference, but maybe it's not so easy. We could compute, I don't know, some sort of distance, so mean square error, absolute error, take the mean and see who is doing better and who is doing worse. I can help. No, I don't help on that. Oh, eventually. It seems that the model 2 is a bit more volatile than model 1. Now let me take out a density prediction for the same series of the two models. So this is model 1. I'm presenting what is called often a fan charts. So here we have the mean prediction, which was the same we had before, 50% and 90% interval. So this is a 95, 75, median, mean in this model is the same, 25, 05%. And those are the red line. Model 1, model 2. Here's when the definition of calibration starts to play an important role. Which of these two will you prefer? So you see this one, the model 2, those are 100 observations, and I'm covering in terms of probability most of them. These one are the same 100 observation, and part of these observations are not assigned high probability. How many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is also 10. So 10 observations over 100 are outside the 90% interval. Here, 1. This is correctly calibrated. If I'm showing you the 90% interval, I should cover 90% of the observations, not 99, as we do here. But of course, sometimes we think more the distance among them, but the distance in terms of density could be different than the distance in terms of Euclidean distance. So that's to tell you, so the exercise is this one, basically. I simulated from a normal, and the mean was 0 and the variance was equal to 1. Then I took 2 models. They were both unbiased, so the mean was correct for both of them, but one had twice the true variance, the other was correct. What is calibration? A prediction is well calibrated is if the probability mass function, the model probability mass function, agrees with the distribution, the sample distribution of the realizations, obviously in the long run. So in my example, there was an agreement. I plotted the 90% interval. I had 90% of the points inside there, 10% outside. We should always prefer a correctly calibrated density. Why? Because it's also telling us another important information. We should never predict the unpredictable. This is not our job, probably. Probably this number are just 1% of the observations, and predicted the 1% of the observation should receive 1% probability, no more than that. So we should be careful predicting the predictable, our like to define. But, you know, there is a literature on that, and let's see how we can build and do more about that. So the calibration is the important point. In this simple case, it was easy to distinguish between the 2 models. It's not always the case. So the general rule will be that we should always prefer a correctly calibrated density, but if 2 densities are correctly calibrated, what do we do? And here is the second part of the methodology and the literature related to that, which is combination. As I mentioned before, averaging has a long history. Uncertainty plays an important part inside here, for example, Bayesian model averaging. What has become more intriguing recently, that we first thought only about simple rules and univariate combination. Now we start to think correlations between variables, also in the combination, and weights that should correlate. So if, just have an example, we have 2 variables, one model that does well for one variable, possible, it should be high correlated also to the other variable, and it could have a higher weight in that sense. Moreover, we start to do combination where we didn't look to all the density, but we just were focusing in part of this density, so regions of interest or quantiles. As I mentioned before, some models may do well in some periods, other models could do well in other periods. Importantly, if you're going multivariate, we should also think that not necessarily the performance is identical for all the models. So we should have a flexibility enough. And then probably a quite nice topic that econometricians jump much later than statisticians is that the open or closed model set. Is the true model inside or not? So we should search for the true model or not. Remember that the BMA is done for the closed model set. It will always converge to a model, assuming it is the true model. Yeah, but if the model is not, if the true model is not in the model set, what are we doing? We are selecting or converging to the wrong model. So these things should be considered. And here I thought to have one selfish, if you want, slide where I review some of my papers. So I think we did a bit of work first in time varying weights, which is the first joint paper you have there, where we propose a distributional state space representation of the problem. So we basically made a latent factor models restricted to the unit. So standard factor models, which was extended to work at least in terms of weights in the unit space. We had the toolbox for that. We did some applications, more or less of the same stuff in nowcasting, in stock market return. We even developed that to work with the larger data sets, something as, I don't know, 7,000-8,000 densities. So there is a bit of issues to estimate all things, again, with time varying weights. And then the paper that, however, is closer to today, and I will jump soon to do that, is this one. Is just a paper where we realize the point of doing density combinations and density calibration in the same exercise. And we had to use two mixtures. That was the game we had. Where one mixture, which was the standard combination, was maximizing posterior likelihood. The second mixture, which was a beta mixture, was achieving calibration by fitting pits. And I will tell you soon what the pits are, but it's nothing more I can already mention. A pit is the inverse of the CDF, and if you compute for many observations, you should have a uniform distribution of them. So you really want to see if indeed you are giving the correct mass to the prediction using the ex post realization. If you put many of them, you look at the distribution, it should be uniform, because you should assign 1% probability to 1% interval and so on. So let me jump in the model, because I have a couple of slides on that. I try also to be less than 1 hour, Tom, so there is a bit more time, because I think online is difficult to stay 1 hour with concentration and so on. So this was, if you remove time here, T, and T, this was the original JASA paper I was mentioning. So here you have the combination, where we basically, what we have, let's work with the CDF. Same could have been done here with the PDF. I usually you see the PDF, but let's focus 1 second on the CDF. You have a set of M different predictions density, CDF, for the variable Y, which we have built somewhat. I'm not entering on the way. And what do you do in terms of combination? You give a weight to each of them. Usually these weights are positive and restricted to sum to 1. So you are sure that you will have a density also as output. And this is the combination. How you compute the weights, it was all the story I was mentioning you before about the model incompleteness, time varying weights, correlation, and so on. Then what is coming in the calibration? As you do for an individual model, this will be the density for the individual model. We thought to do the same. Okay, let's do the combination. And then let's see if the joint density, so the one done by the combination, has good or not property. If it has not the property we're looking for example, we can apply a beta distribution, such as that I can change this mass to satisfy the calibration properties. What does it mean? If I have too much mass in the central part, this was the exercise, so you see, this is giving too much mass in the central part. Probably 95% of observations are in the 50% interval. So what should I do to do that? I should remove some sort of mass where I'm wrongly calibrated, in the tails. So I should take away from here and move to other part. So I should reduce my stuff. So here I have too many observations inside, too few there, I should do the opposite and remove in mass and put in centrally. So make a spike that distribution. And how do we do that? Via this beta distribution. Why? Because the beta is limited from 0 to 1, so it works well with the CDF. And if I take a bit of mass from one side, I can move from the other. Depending on alpha and beta, I can have a lot of shapes inside there. So I can be quite flexible. What is the original? Eventually, in the Joseph paper, we had another idea because the recalibration has been introduced by Gatling. What we said, okay, why do you want only one beta? It might not be enough because you need to basically recalibrate all the support, so all the density with the same type of the distribution. But maybe you will prefer to recalibrate, I don't know, the left tail in a different way than the right tail. So we use a mixture of betas. So we had not only one, but we had a mixture of them. Anyway, returning here. What we thought to extend in this exercise? We thought to add time varying alpha and beta parameters, so the two parameters of the beta, plus time varying weights. So here you see there is alpha t, beta t, those are the parameters of the beta, and omega it, which are contrary the weight that we assign to each of the individual forecasts. Here are the elements. As I said, this is in PDF. The same things can be written in CDF for, sorry, this is in CDF, this is in PDF form. There is one-to-one, of course, mapping of them. Okay, that's nice. And I always want to do from the beginning, maybe you understood why, because myself introduced or pushed the literature on time varying combination 10 years ago, and then he wrote a paper on calibration and combination that had not time varying weights. The question is, how do you do that? Because remember, just in a simple exercise, I don't know, 10 models, you have 10 weights to estimate here, plus other two parameters. And you need to estimate from forecast. So you need quite a lot of data. First, you need to estimate the model. Let's say that we use a completely model-based approach. You need to estimate the model. Predict, create this F. Predict long enough, such as that I can estimate this model, and then predict with this model. So data becomes important, and fitting a beta is not easy. So it's not, you know, we already understood that we need a bit of data. So macroeconomic applications, for example, were not good. Here at that paper, we were focusing on weather and financial applications. And now I'm telling you, I want everything moving. And then, you know, the risk to over parameterize the model is extremely large. So the way we decided to follow was using a score-driven approach, which is what you have in this stuff here. So let's assume that we put all the parameters, alpha t, beta t, and omega t, in this theta t generally parameter set. It has a dynamic, which depends on the past. For example, it could be some sort of random walk approach. So it depends on the previous value, an error term, plus two extra elements here. The first one, the Whorf here, is a time variant parameter. The UT, which is moving this stuff, and which specified then later on G, is defined as the conditional score vector, with respect, of course, of the parameters that I want to move. Let's give the exact definition of that. Here you have, if F, which is basically the stuff we have here, in this case, is the model I'm looking for, I could think that, for example, the log likelihood condition of this parameter is what I do want to maximize. So I'm looking for parameters values such as that the log likelihood of my PDF model, so the two here, is maximizing. and I'm imposing variation, incremental variation, depending on this. That's how, in brief, I will define the score-driven model. I can decompose or work a bit more data if I go to redefine carefully theta by taking advantage of saying part of this can move, part cannot move. So call more generally some sort of epsilon here, and I will have this core function. Why? Because then the conditional likelihood is always the same. And I can make deciding what is varying via this function here that could have this structure. So you see the structure will be, is an autoregressive type of structure with a constant element here. So there is a variation from the previous value. There is an error that it can push up and down the variation. And plus there is this time variant parameter, which is case sensitive and is basically the long-term mean of the process. So basically what I'm suggesting you, we make the time variation depending on the score. And we model the score with what we got used. So the score is driven by something that I'm able to control. For example, this sort of autoregressive process, only that it is not on the parameter, it is on the score. Why? Because I can group parameters in the score. I have a lot of flexibility by doing that. And indeed, let me give you some examples of how things are. So for example, I could only have a time varying calibration functions. So the weights will be constant. The model weights will be constant. Part of the learning will be constant on the score driven. And the two things that will only change are the beta parameters. This function here, or the core part of this, will assume this structure. I'm not going to read. I mean, hopefully the paper, I will be able to finish the paper soon. Believe on myself, you just need to take the conditional likelihood and take the first derivative and it comes out. So it's a formula, nothing extremely difficult. The intuition here is that you decompose the parameters in two parts and it depends on what you want to push more. The second element, time varying combination, on contrary. This time I keep invariant the calibration and I make changing only the combination weights. This will be how the score, the score function, the score driven function will look. So it's a slightly more complex of the previous one that we had, but you know, there is a closed form solution also for that. So you see, from varying everything, I start to have rules for making varying something. However, I'm still with only one calibration density, only one beta. Maybe I could also think that I could extend this to have more calibration density. And here, you see, previously I had just one F. Why not to use KF and giving a weight to them? So here is what I told you, the mixture of the beta is an example. So I make two mixture, a mixture inside here, which is this, or this one in PDF, and a second mixture over that, with of course some restriction to make sure that things are going. That's definitely possible. If it's static, it's even easier. Why? Because you decide how many Ks there are. You estimate K minus 1 weight of the mixture, and you can go again doing by taking the score driven. So you add scores or you remove, sorry, you add the no, it's fixed the K. You take the K elements and you estimate the weight of them by a conditional likelihood approach and by taking the increment of each of them. And the K mixture, what is the residual one, what you have here. Or you could have a dynamic adaptive mixture model, which is the most complex model that we have, where, for example, if you only have two mixtures, which are often called regimes. Why? Because there is this paper that introduces the DAM, how it's called DAM. So you can think the mixtures as two different regimes and estimate the probability of the two regimes. The two regimes can be, by the way, overlapping. So they are not as independent as in other cases. Why is it flexible? Because we know everything how to work with the regimes, which is easier than working with the mixtures. So you could think that you have these two regimes in this framework. There is a formulation for the score driven about them. And in this paper, in this model, in the question 6, what we will have? We will have two. The combination will be the same inside here. But these two functions could be different. Why? For example, could vary alpha and beta. And then we will have this one. And the same weights here. On contrary, we could have only the weights change. And alpha and beta the same. And in that case, the weights will change inside the two combination scheme. So they will be different, possible different inside the two combination schemes. Or you could have alpha 1, beta 1, omega 1, varying all of them, alpha 2, beta 2, omega 2, varying all of them, adding a t. And you give a probability to each of them, and you estimate with that. This is not the final model. The last one, which is the most intriguing, when you have a k of these regimes, they're still fixed, and there are more than two, but you need to decide the number k that you want inside. Usually this number is not extremely large. This will be the score function driving that. So it's slightly difficult, but it's not dramatic. In the paper, we have more derivation. So what I want to tell you, returning to the original problem where we start from, with just one beta, you have alpha, beta, and the omega varying. They give flexibility. It might not be enough. Why? In particular, when you focus on different regions of interest, it might be that the calibration is not enough with only alpha and beta. So you could combine more of them. And we have a formulation that can take up to k regimes. What we don't do here, that could be an extension, we could go to infinite number of regimes, so an infinite mixture of betas, for example, and estimate the number of them. So the moment we fix k to some level, this is definitely an option, and maybe we leave it for the future. That one we thought in this paper was. I mean, we have no thinking to do in this paper. This approach. I think then my experience in the Joseph paper, static version, we added that estimate. The question is when to stop. So just to say a number, 9 is really different than 10. For sure, 9 is different than 18. But one more, one less is where there is the problem. And the conditional likelihood could be informative, such as not. So imposing the rule is the difficult approach in my view on that one. In that paper, we were using a Bayesian approach, and we were basically relying in Bayesian on parametric, and it made everything quite smooth and easy. In this paper, it's a different way of doing. So in the last 10 minutes, so I'm on time by 4, and so we can have some questions. I'm sorry, I forgot. If you want to stop me, if you have any questions, please intervene. So on. I'm sorry about that. I have two screens, as you can see. I have was the camera on and the room in one screen, and the slide in the main screen. So I thought to push forward this paper, this application, which refers to wind speed prediction. specifically 15 minutes I had the wind speed prediction in 2011, January 2011, in Galicia, which is top north of Spain, where there is a lot of wind. And the reason I already mentioned to you, I think there are issues for at least wind powers to predict the wind speed, and that's why they are limited in some sort of use. And I think in the future we need to solve that. And in particular, what you will see later on with my results, my feeling is that they are not well calibrated forecast. So on average, they are okay, but they don't understand where they do the mistakes. There is one specific part of the distribution where it's easier to do a mistake. So that was what motivated us. We took 4 standard individual models. I think 3 of them are pretty easy to understand: the AFIMA, the ARMA, and the ARMA-GARCH. So anyone of us probably has used a bit of this type of model. A GAR-GARCH is an extension of the AR-GARCH to be fit really to wind, because the wind, the wind speed goes from 0 to infinity. So it's not continuous variable. And also, if you look at the distribution, it has threshold. There are periods of very low wind and periods of very high wind. So usually it's bimodal, the distribution of the wind. So the GAR-GARCH, which I'm referring to the paper Capolina Press, if you want more information, try to take advantage of this. So it's introducing nonlinearity in a different form than the previous one. We will do 2 combinations, the standard equal weight. So we will do density prediction for each of these models, show the evaluation about that, combined by using equal weights or combining using the most advanced method, so this one that we have in our exercise. So everything is varied in the exercise we have. Let me first show if we are doing a good job or not. So I thought, so here we are doing density forecast, and I'm presenting you the results in terms of predictive likelihood, or if you prefer to call it some sort of exponential of the log score. So if you take the log, you have the log score of this stuff, which is a measure of distance. Density forecast is a click Kuhlmann-Leibler information ratio measure that you can use. Larger is the value, better the model is doing. So you should not think in terms of, mean square error, that smaller is good. Now here is in terms of probability, larger it is. And as you can see, the DCC, how I call my model, but probably I should change name. It was too close to a GARCH model. Does much better than all of them. In particular, since we use, I haven't presented you the estimation algorithm, but since we use a simulation to estimate that, not only I have the mean, but I can take an interval of the log score, because I will repeat my exercise many times. So I can compute draws of log score and have a distribution for that. So here I'm showing you the 90% of the distribution. As you can see, all these models are out of the 90% distribution of my model. These have only one log score, because we only simulate once the density. Here we do more draws for that. And in any case, it seems to be really superior. And I thought it was a nice result. Now let's move a bit more on the output of the model to try to have an understanding and some intuition where the good performance is coming from. So first, I'm showing you the combination weights, and I average across the regimes in this exercise. This is, no, I think, sorry, I'm presenting the result with only one regime. I'm sorry, I made a mistake, because otherwise this graph will be double. So I thought to present only this. So for each of the model, you have the distribution of the weights represented by the mean and the 90% interval. As you can see, the gauge seems the one to receive in some periods most of the mass, but it's not always the case, and most other times is really stable in the mean. Then there is some sort of change in performance between the ARMA and the ARMA gauge, as you can see here. So the gauge really goes down in some periods when the gauge goes up. So this instability is useful, see, goes up, then the ARMA goes down. Basically, the model is telling you one of these two you should use. On the contrary, the ARMA is the one more on average. The ARFIMA seems not the way to work with the wind speed, at least looking to the weights in our model. So the type of time varying volatility for wind speed does not seem a standard ARFIMA approach. But now I want to tell you a bit more, and I'm sorry I cut the time here. Anyway, these are 2 days, basically around, I have 15 minutes, so 4 observations, 4 hours, so 100 is more or less a day, just to give you an idea, 80, and these are every second day, basically, in the scheme. And I'm showing you the time varying alpha T and the time varying beta T. So the component of the mixture. Remember then when the values of these two are above 1, what it means? We are skewing the beta distribution to the top, to the large values. And what is happening here? It's exactly that. So our recalibration is suggesting that all the models and the combination itself is giving often too low weight to the top tail of the wind prediction. So the prediction are not accurate enough in telling us when we do have a strong wind. And it's, it's always difficult to say if it's the alpha or the beta or the beta distribution that is pushing that. So the indication here would be the same, and it's how much you push the combination of these two. Most of the time you see they are very similar. So it's really pushing mass, nothing more. Sometimes there is a divergence how it does on that element. I think this is important because, the message I can give, at least looking to this model to the wind speed, will be careful because there are some periods in the night. So most of the time, but in particular some periods in the night, here is the night, where really we are biasing the prediction too low. So the wind will be too high, and you should take benefit about that. You could go continuous. It will decrease the wind, fine, but it won't stop in 15 minutes. The question that it can decrease of 20, 30, 40%. However, the prediction is by far too low in what we have. So we should have stronger with the prediction. So with this, what we have done, so I can finish exactly at 4, even if we start 10 minutes later, but I was sure I could have speed up a bit. We think we have a new dynamic combination calibration scheme. It's extremely flexible, as I mentioned you. You can really play with the time variation in the weights, in the calibration, in the mixture, in everything about them. So I give you some sort of examples. In the paper, we have simulation examples to show you how it functions and so on in practice, and maybe if you should prefer one type of approach to another one, where to introduce the time variation. Then we have an application, and we think that calibration is crucial for weather predictions, in particular for the wind, where you want to know if the probability of being in high wind speed is high or low. It's not just the amount of wind, because in any case, with wind, let's say with the wind above 10 meters a second, whether it's 10, 20, or 25, is irrelevant, because in any case, the windmill will move. So the important element, if there is or not a wind, that's probably more important element. Returning to the model, I already mentioned via the score wind, the score driven approach. As I said, we do show that our dynamic combination calibration model outperforms standard individual models and also simple combination schemes. And probably the most important result that I have in the paper is that calibration seems to recalibrate predictions to high values. As we were mentioning, it seems that it's difficult for standard statistical econometric models to assign a lot of mass to large values in the exercise we have. It would be nice maybe to test if it's also true in a, in a country with a lot of wind in a period where there is not a lot of wind at the moment.
Thank you. What are the models you're combining? I didn't understand that. Is it the same model with various settings?
No.
Is a series of different models?
So sorry, I was a bit fast on this because I don't want to have many slides, but of course I should provide more details on this. I apologize about that. We have 4 individual models. One is an ARFIMA model. So it's the integration that we go to estimate every time. Every time we do a new prediction, these models are all estimated. So every 15 minutes, basically we rerun these 4 models and we make a new prediction for these 1,000 observations that we do have. The first one is an ARFIMA that we have, so it's the level of integration that is important. The second one is an ARMA, a standard ARMA model, and I think we set the maximum P and Q to 7, and we select them, or sorry, not 7, because these are not daily data. We go a bit larger because we want to have some hours in the sample, so I think is to 24, so it's 4 times 6. So yes, probably 24 is the maximum legs, and we selected them. Then we have an ARMA PQ Garch 11. So we fix the Garch to 11 in this exercise. The Garch removes the MA part, this type of model, and introduce some sort of threshold in the AR part to create this bimodality that I was mentioning. It still has the Garch, and also it has a restriction such as that the wind speed cannot be negative, because these 3 are not restricting. I mean, there are no restrictions for these 3 that the wind speed could be negative, which is impossible because I mean, the wind speed should be at least 0. But we thought to use. Those are the 4 models.
Could you go onto the slide with all of the colored lines on it?
This one or this?
The first one. So I was wondering why, in particular, when the green model goes high, the blue model goes low. Like in particular, the blue model, it's obvious that the other models should go low since the weight of the green model goes high. But why? Could you give some intuition as to like
Absolutely.
why those 2 are like coupled?
No, it's a good point, which I'm thinking how to represent. I can tell you easily, but to represent is slightly different. It's due to this possible bimodality. So when the wind goes really up, this model does better because it pushes one of the 2 modes much higher. The ARMA has too much history, is slower in moving. So the Garch will help to take part of the time varying volatility and the large volatility we have with the high values. But still the MA component and the array component will keep inside too much persistence. So what happens in our combination, when I need to increase before doing calibration, I also try to see if I can work with the weights. So I do realize that the green is, wind is going up, green is predicting up. So what I do, I give most of the weight to the green. The other one, in one way is not able to do the same, and probably is it has a bit of the same pattern, but not the same speed to react, so I do reduce that. Why you will say I keep the armor maybe in, because it's an average if I make a mistake. So that I prefer to have average one inside that. So that's my experience. Probably one way that I could show this is by showing, because if I put the prediction, the density prediction in a graph, it would be a disaster, because these are every 15 minutes, 1,000 observations, you don't see anything. I could put the series, so one could see, or the volatility of it, not the series itself. So that could explain when one is receiving more weight and one less. So thank you.
Okay, thanks.
So I have a question on always the application. I was wondering what guided the choice of these specific models and what guided the choice of having 4 models and not say 3 or 7.
Okay, so this paper. The one that introduced the gauge, this one, we took basically from them. So I should be honest that we haven't investigated more. There is a huge amount of new models coming in this, not only with the speed, but also with the direction, because for someone it's very important also the wind direction. We thought not to take in also the wind direction. We make it too complex, the paper, and the first part is already quite challenging in terms of formulation, so on. I just show you the summary. So this was the idea. We took one standard paper and we show how our method is functioning.
Okay, thank you.
Pleasure. Thank you.